Ah, horses, wonderful and powerful. Horses have been an important part of our civilization for a very long time, until they were substituted by engines. Still today, our engines the output are measured and estimated by horsepowers. Welcome to Lecture 03. In this class, we'll talk about the physical meaning of power and how we can understand its concept to solve problems. Is 1 horsepower literally estimating the power that an average horse could deliver? And surprisingly, the answer is yes. Now, a 1 horsepower, its definition is 746 watt. Now, to understand what it means is we have to go back to history a little bit. And the person who came up with this analogy is James Watt, the very inventor of the steam engine, and whose invention basically powered the Industrial Revolution from the mid-17th century. Now, James Watt wanted to come up with a concept, a sense of comparison, to show to the people how his new machine, was more efficient than horses and other animals. So he wanted to estimate an average workload of a horse in 1 workday. Now, the 1 horsepower is not a measurement of a momentary peak, because a horse momentarily can produce a more output than 1 horsepower, and even humans momentarily can produce more than a horsepower. A horsepower is defined such that in a sustainable basis, say that a horse is plowing a field with such a work output that he could do that throughout the entire workday. And we do take the average of that, and that is the estimation of a 1 horsepower. In today's definition, 1 horsepower is 33,000 pounds being lifted up from the ground 1 feet height in 1 minute of time. So it is a power output in time. So, and that definition in today's standard, it was pretty close to Watt's estimation back then. Now, today we define, as I mentioned earlier, that 1 horsepower is 746 watt. Now, 1 watt is a unit of power, which is 1 joules per second. It is, you can see already here, is an energy rate. Is the energy, how much energy is being delivered per second. To understand this concept of power, let's go back to the definition of work. Okay, so the work is a transfer of energy in a given system. So the work either changes an energy or it transforms an energy from one form to another in a given system. The power is at which rate this energy transfer occurs. Because many times we're often interested in how quickly that transfer takes place. And that concept is power. The rate at which energy is transferred or transformed is called the power P. And here, in a mathematical expression, power is change of energy in time, which in the scope of our lectures, we will consider that power is delivered by change of work in time. Now, before we delve into mathematical expressions more, let me give you a physical example. So take a look at the figure on the right-hand side with a light bulb. Now, 100 watt is a common power that is used in a light bulb in everyday household. When was the last time you have changed a light bulb, a fluorescent light bulb? And why did you change it? And the reason is probably the filament burned, and it may be disconnected even from the heat it was generated. Okay, so what caused that heat to disconnect that wire, and how does it relate to the power? Well, 100 watts light bulb, that represents an electric energy being consumed as light and thermal energy at a rate of 100 joules per second. And so the bigger the number of watt, the more power or more energy is being consumed, in this case dissipated or wasted even, as a form of eliminating light and the temperature change, the thermal energy, at a rate of that output. And to give you an example, I have here an LED light bulbs that I use in my household to change broken light bulbs. Now you can see on the top here a 60 watt replacement, and on the bottom here you read the number that each of this light bulb has 8.8 watt. Now 8.8 is a fraction of 60 watt lamp. But this LED is much more efficient in a way that it could provide the brightness that is equal or even surpassing the fluorescent light bulbs using 60 watts of power. So this is saying that if the light bulbs have to use 60 watts, 60 joules per second energy transfer to give out this brightness, and then if, let's say, you have a light bulb that is even 100 watts or 120 watts, that much of an energy consumption is going to shorten the lifetime of the filament or the sockets that are involved in the light bulb. In comparison, the LED only uses a fraction of the energy transfer to provide the brightness and that we desire. So in this case, we see how the concept of power is being utilized. And of course, that leads to, in this case, I'm guaranteed that this functional light bulb could provide me 13 years of lifetime. And that's definitely much longer than the fluorescence light bulb. And what allows that technological advantage is, of course, the technology behind LED, light emitting diodes. And to understand the concept, it is in the realm of solid-state physics. But remember, it is a development of the physics and experimental physics that leads to the inventions of the LEDs that we use in every day. All right, so this concept of power, as you can see, is very, very relevant in not only in physics, in industry and in engineering and applications. So go back to the figure here. We talked about the light bulb here, a gas furnace that is responsible for boiling the water and providing hot water in the household, uses about 20,000 joules per second. So it has a power output of 20 kilowatt, equivalent to transferring or consuming 20,000 joule of energy every second that is being used. In the middle of it here, I have a picture of a truck. Let's take F-150 as an example. We know that the truck engine is a combustion engine. So inside of that cylinders, we have a combustion, the chemical explosions that is being translated into turning the torque as a torque, that is turning the axle and delivering as a kinetic energy of the truck moving forward. So there are many different work being done here, transferring the energy type from one type to another. A typical power output of a truck engine is 325 horsepower. And now we know that 1 horsepower is defined as 746 watt. So now we know a truck engine of F-150 could deliver a power output of 242,000 or 242 kilowatt of power. This is how much energy is being consumed every second, turning it into a kinetic energy of a truck. Okay, so I hope these examples somewhat solidify conceptually excuse me, what a power is. Now let's go into a little bit of mathematical derivation. Here, I'm starting here, power is equal to change of energy in time, which in this scope I mentioned that it will be a change of work being done in time. Okay, now the definition of work in its most compressed form is the force vector dotted with displacement vector. So let's consider this force a constant force for now. And that force is being applied to move a certain particle with displacement described by this vector. Then dW would be force vector dotted with dr. And that is because if I want to talk about infinitesimally small work being done, that is to say that displacement is infinitesimally small applied to that same force. Okay, so here dW is F dot dr, and then we take that time derivative of that. And of course the force comes out here, and this is still a dot product here. You have dr dt. Now what is the derivative of position in time? Well, that is velocity. In this case, velocity vector. So here you have force vector dotted with velocity vector. And remember from dot product from lecture number 2, look at the figure here. Two arbitrary vectors, force and velocity with arbitrary directions, will have an angle between them of angle theta. Then the dot product is defined as the magnitude of the force times the speed, the magnitude of velocity, times cosine of the angle between. And that is how you calculate the magnitude of force. Okay, now let's go back again, conceptually. Power is how much work is being done in time. It's how much energy transfer occurs in time. And that, we plug it in, the definition of work, is infinitesimally small amount of work, and then that leads to the force vector dotted with velocity vector, which is Fv cosine theta, that is equal to power. So this is a mathematical way of interpreting power, but just remember that power is a rate at which energy is transferred in a system. Okay? Let's take a look at example 9.11. A power output of a motor. A factory uses a motor that is a cable to drag a 300 kilogram machine to the proper place on the factory floor. What power must a motor supply to drag the machine at a speed of 0.5 meters per second, and the coefficient of friction between the machine and the floor is 0.6. Now in this case, we are given that the machine is being dragged at a constant speed of 0.5. That tells me that the net force here is 0. What are the two forces being involved here? We have the force of the motor that is dragging the machine. That is counteracted by friction, and that is equal to 0, so that we have an expression for the force of the motor in terms of the kinetic friction, that is mu k mg. And in this case is 0.6, 309.6. And we of course already know the velocity, that is 0.50 meters per second, and power is the force vector dot product with the velocity vector. In this case, they are parallel, so the angle between them is 0. So Fv cosine theta, this part becomes 1, theta angle is 0. So this is simply F, the magnitude of the force, times the speed. In this case, that is simply 0.6, 309.8 multiplied by the speed, 0.5. And that should give us the answer of 882 watt. That's not that difficult. Now, there's one concept that I need to emphasize here. Often, power is measured in terms of consumption and dissipation. For example, a light bulb is an electric energy internally being consumed outwardly as a light and thermal energy at a rate of 100 joules per second. A gas furnace is a chemical energy of gas internally output as a thermal energy, consumed as a thermal energy at 20,000 joules per second. So oftentimes, power is described or measured in terms of consumption, the output consumption. And this is why in this case also we have the friction force here being involved. But it's important that we don't deal friction as an individual force, because technically the work concept is derived from Newton's second law, which is a sum of forces, net force, acting on a single particle. Now, the friction force is not a single entity. It is an averaging force acting on many, many particles between surfaces. So we cannot describe the work done by the friction directly, nor talking about so the only contribution of the friction that we could see as an output is that it dissipates energy. For example, let's take a look at this example here. Let's say that the total work done by this machine, if there's no friction, should translate into the change in kinetic energy of that machine, right? It was starting from the rest, changing from velocity equal to 0 to that speed, the final velocity. That's the total work being transferred in terms of kinetic energy. However, when there is a friction, it's a different story, because some of that work being done will be translated into an energy that will be dissipated, and in most of the time it is in a form of a thermal energy. Okay, so here, because your work is now divided between the kinetic energy and the thermal energy, and this here is caused by the friction, you have a final amount here. You have a division. You have a dividing of that work here. So you will have a smaller kinetic energy because of the presence of the friction, and that amount that the friction causes is what dissipated out of the system. So often the power is then measured in terms of its consumption. It's an output. And this is all that I'm going to talk about in terms of dissipation in the section 9.5. That's all you need to know. The friction is considered a dissipative forces. It is not a single entity of forces that you can calculate or work directly out of it. But in the process, this friction will dissipate energy out of the work done being transferred, so that a total change in kinetic energy will be reduced by the dissipation that's caused by friction. Okay, you can comment or post questions when you're dealing with this, but for the lecture for this time being, I want you to focus on the power concept for this lecture, and that the power is measured in terms of consumptions and dissipations often. All right, let's take a look at more examples to solidify that fact. All right, so here, how much energy is consumed by 1.2 kilowatt hair dryer for 10 minutes? Okay, so here the definition of power is change. Is how much energy is changed. Okay, well, we actually here we're already given here the power is 1.2 kilowatt. Okay, and for 10 minutes. Now this, of course, is 12,000 joules per second. And this being used for 10 minutes, meaning 12,000 joules per second multiplied by 10 minutes times 60 seconds. And here you have 12,000 times 600, so divided by 1,000, you have 7,200 kilojoule of energy is used in this example. Again, a 10-watt night light left on for 24 hours. 10 watt is 10 joules every second. And 24 hours is 24 times every hour is 60 minutes times 60 seconds. So again, we have this big number here. (864 kilojoules of energy is being consumed by this light left on for 24 hours. How about this one here? How much work does an elevator motor do to lift a 1,000-kilogram elevator a height of 100 meters? Okay, let me draw here. All right, so just draw a situation here. An elevator, a motor is pulling this up this way. You have to overcome the force of gravity as a force of the motor. So here we know that the sum of forces is this, and we want to know what's the minimum work being done here. We set that equal to 0. This tells you the minimum amount of force it has to have to overcome the force of gravity. And in this case, the force of the motor is, of course, equals to mg. Now, work done by the motor will be simply the force of motor times the displacement. That's a definition of work. And in this case, that is going upward, and also the displacement is also going upward. So they will have a positive amount of 1,000 kilograms times 9.8 times the displacement 100 meters. So you will have here 98 2, 3. Oops, let me down here once again. There. That's the amount of energy work is done by the elevator. The second question is asking how much power must a motor supply to do this in 50 seconds at constant speed? Well, that is very simple. The power is the rate of work being done in time, and the work is that amount. We want to do that in 50 seconds. So that will give you (196,000 joules per second). So watt. So 196 kilowatt will be the answer to that question. Okay, now to finish this off, let's take a look at this example here. 4 students run up the stairs in the time shown. Which student has the largest power output? Okay, so for student number A, you have this work will be done by gravity, by the way. So you have the weight, 80 kilograms times 9.8, and this would be done, work done by this person, have to overcome the gravity, and here you have the displacement of 10 meters. And you divide it up by the time it takes, which is 10 seconds. Here you have the same person same height, but it's done in less time. Here you have 64, 9.8, 10 meters divided by 8 seconds. And here you have 80 kilograms overcoming 9.8, but this time the displacement is larger, but it also have longer time. So you calculate the power for each individual here, and you will compare which one is the largest to the smallest. I think I'll leave the rest of the arithmetics to you. Now, that concludes this lecture on power. Now, if you have any questions or comments, feel free to leave it on the YouTube channel, or you can also visit one of my office hours. Thank you so much for your time and for your attention. See you next time.